Okay.
Okay.
So Tim, you're now a presenter.
Show my screen. Okay.
Yeah, I can see your screen. Let me see what I'm.
And do
Okay,
I
I'm
need to
sorry.
turn my camera on? Probably, right?
So you don't need your. Oops. So you don't need your camera on.
Okay.
Let me just.
Do people usually have it on or not? I mean, I don't know. I don't see it. Oh, I see there, right there. People can see you. There we go.
Yeah, they can see you. They don't have to see you if you don't want to.
That's fine. I mean, it's not like I'm just I just crawled out of bed or something.
Okay. I don't think I have. Yeah, that's fine. So I'm going to. I don't think. Testing 1, 2. Oh yeah. So this is going live to everybody. So I'll be handing it over to you. I'll be doing an intro, Tim, and then I'll be handing it back to you. So right now it's on my screen, and then I'll be changing the presenter to you.
Okay, perfect.
And I'll be changing that over to you, and then when we're all done, I'll change it back over to me.
Okay.
Okay, good. So I'm going to put everybody on mute for now, and then I'll come back.
Sounds good.
Thanks, Tim. Good afternoon, everyone. Can you hear me? If you can give me a thumbs up or write in your questions that you can hear me. Tim, can you hear me okay? Give me a thumbs up.
I can hear you.
Okay, wonderful. Okay, I want to welcome everybody today. Welcome to Netch Instruments and our new Research Spotlight series. I am your moderator, Peter Vikos, and these are our virtual presentations on a wide range of applications where users demonstrate how thermal analysis contributes to their research. Today is our polymer science session. Over the next 2 weeks, we'll be offering presentations in metals and nuclear materials. You can write your questions in the questions section located on the toggle bar on the Go to Webinar, and we will answer these questions at the end of the meeting. Our first in this series is on polymer science. Let's get right into our session entitled Thermal Analysis and Dynamic Mechanical Analysis of Dual Curing Resins in 3D Printing. This will be given by Professor Tim A. Oswald, co-director of the Polymer Engineering Center in the Mechanical Engineering Department of the University of Wisconsin in Madison, Wisconsin. The polymer engineering activities at the University of Wisconsin first started and started the first engineering plastics course taught in this world. Current research interests range from traditional plastics and polymer metal composites to bio-paste polymers. These activities have made the Polymer Engineering Center at the University of Wisconsin one of the nation's strongest research groups in the area of mechanical engineering, polymer engineering, and polymer composites research. The Polymer Engineering Center uses several material characterization techniques across a wide range of research topics. This presentation will briefly describe how thermal analysis and dynamic mechanical analysis have been used to optimize the manufacturing of dual curing resin systems used in 3D printing. Professor Oswald, I'll turn this over to you now. Let me first start by sharing your screen. Okay, Professor Oswald, we can see you and your blue screen. There we go, perfect.
Okay, well, thank you, Peter, for inviting me, and thanks everybody for showing up. I understand it's a lot of people signed up, so I'm glad this presentation is not this evening. Otherwise, there'd be just one more competing against Biden and Trump, and so that's good that it's in this afternoon. So, anyhow, so I think I changed my presentation just a little bit. I'm calling it thermal analysis and DMA, and I have it divided into two parts, one on dual curing resins and additive manufacturing and hybrid structures, and the second one is characterizing natural rubber, which should be also a really interesting one and maybe of interest to some of you, but application would apply to other things other than natural rubber. The two graduate students that actually basically did all the work and helped me with this were Alec Redman and Alan Roman. So I thank them for all their help, and I get to present it and take credit for everything. So First, let me start by introducing you. I think I just did something funny here. So by introducing the Polymer Engineering Center Characterization Lab, we basically call it the NETCH Lab. We have a lot of equipment from NETCH. I will be talking, of course, about the DMA, the Eplexor machine. Oops, I misspelled NETCH here. I forgot the E. Sorry, Peter. We also have a DSC 214 polymer. We have a TGA thermogravimetric analysis. We have a dielectric analyzer, and we have an LFA nano flash to determine the thermal diffusivity and other thermal properties. And I won't talk about neither the DEA nor the LFA, and that may be for a different talk. We do use all of them a lot, particularly DEA. We do use also to characterize curing reactions and chemistry and materials, which is a whole different area of quite a bit of interest. Oops, sorry. So the first part of this presentation is the kinetic study for additive manufacturing, optimizing the thermal curing cycle of EPX 82. The work was led by Alec Redman, my graduate student, with two of our visiting scholars, Paul Ullman and Lukas Kagemeyer, who visited us from Germany for a period of 6 months each and worked with him in this project. And what the project applies to is to a process, additive manufacturing process called digital light synthesis, or DLS, that used to be called CLIP, continuous liquid interface processes. And the way this process works, and it's a machine. We have a machine that is given to us by Carbon Inc. in Redwood, California. The way this works, the additive manufacturing system has a window that is oxygen permeable, which saturates the surface near the window with oxygen, which hinders the curing with UV rays. And so it creates a dead zone, which allows for the infusion of for the flow of the liquid under the build as the platform moves up. And basically, you can project as close as possible, as many pictures one after the other one, down to micrometer type movements. So the layer size is much, much smaller. So compared to traditional VAT polymerization processes, where you can actually see the layers, that you can hardly see them with the DLS process. Also, it leads to a part that is relatively isotropic, so the anisotropy is very, very slight in this process. The way this process works then is as I mentioned, it's a dual curing process. So the chemistry is a little bit hidden and it's not known. So it's a secret at carbon, but we know that part of the molecular structure polymerizes with UV, and then the second part of the curing is with heat activated cure. So there's a switch in the cross-linking process as you heat up the material and finish the cure. So the step one is what comes out of, after step one, the part comes out of the printer, and that's the green part. It's the part that was cured with UV rays, and then in the oven, you finish the cure, which is an extensive curing reaction, which is a thermally cured part, and you actually make a part at the end that is very stiff. Is 2,800 megapascals or 2.8 gigapascals, and it has an ultimate strength of 82 megapascals, and it has a relatively large elongation at break, and could work for very high temperature applications. So the question is what we wanted to do with the parts that were printed is we wanted to optimize the cycle, the thermal cycle. So currently, the picture that you see here is the steps that need to be taken to take care of the thermal cure cycle. with very, very slow conversion rates and very low maximum heating rates. Maximum conversion rates are about 0.6% conversion per minute, with maximum heating rates of about 1.2 degrees Kelvin per minute. This is done for two reasons. One, we don't want to heat it too fast and soften the material before it starts curing, thermally curing, and start sagging. And the other one is you don't want to create high residual stresses during the curing cycle. However, a view into the actual reaction, the thermal aspect of this reaction had never been done. And so we figured this very, very long curing cycle, almost 13 hours, is unacceptable for applications, so for industrial applications. And particularly there, automotive companies using this to make components, like for example, BMW uses the DLS process, or uses the carbon machines to manufacture some of the components for the Mini and other components in BMW. And so 12.5 hours is a relatively long cycle time, which is very expensive when you mass produce parts, and it becomes prohibitive. You need too many machines to produce the parts. And so the objectives of this particular project was to optimize the thermal curing cycle time using a kinetic analysis, and then validate the final mechanical properties of the parts produced with a new curing cycle. So we want to cure it faster, but we don't want to have parts that sag. We don't want to have parts that have too high residual stresses, and we want to have parts that actually have the same mechanical and thermal properties. And so that was the main goal of our projects. We used thermogravimetric analysis to see what maximum temperatures the green part could have. We used differential scanning calorimetry to characterize the curing reaction, and we used the NETCH kinetic analysis software, and then we used dynamic mechanical analysis to characterize the mechanical properties of the finished parts. So to do the thermogravimetric analysis, we used NETCH's TG209 Libra machine. We took a sample from stage 1. So after the UV curing reaction, the sample size was 10 milligrams, and we used a heating rate of 5 degrees Kelvin per minute. And you have some information underneath there that you can see. So here's the result of the analysis. On the left-hand side is the mass of the sample. On the right-hand side is the change of the sample per minute, percent weight per minute, and we see here that we have a degradation temperature of around 398 degrees C, and that gives us an idea. There are, of course, some losses of volatiles and other things that occur here in this process. So once that was done, then we did a DSC analysis to monitor the curing reaction. We used different heating rates, and one uses different heating rates to be able to capture all the events that occur. Since in this case, we were shooting in the dark, we didn't really know the actual chemistry. We still don't. I mean, we know the general chemistry of the material, but the exact chemistry of the material is not known to us. And so we needed to use a lot of heating cycles, heating rates, to be able to capture all the different events, chemical events that are exothermic, that take place during the reaction. And again, we put in samples after stage 1, so the UV curing had already taken place, and that's a whole other story, is how to characterize the UV curing stage, and that can also be done with NETCH equipment, but it is not part of this study. A sample size was also about 10 milligrams, plus or minus 1 milligram, and we did a temperature range from 0 to 325 degrees C, and we did heating rates between 0.5 degree Kelvin to 5 degrees Kelvin per minute. And here we have the results of all of them, going from 0.5, 1, and 2, then 3, 4, and 5. And again, you can see the baseline, and you can see the deviation from the baseline, which is the exothermic reaction, curing reaction. It's very interesting. Here we basically just capture sort of one kind of general autocatalytic reaction, but as we speed up the process, we see that we start recognizing at the beginning and at the end 2 shoulders, which represent two other reactions. So you can see that here, you can see a general reaction, which is the general hump, and here, but we see a shoulder here and a shoulder here at the beginning. And so here is where that Netsch offers comes into the picture. This is Kinetics Neo, and we've worked with Netsch now for years. In fact, I've had 2 PhD theses that have actually worked with Netsch testing these pieces of software, and I believe is probably the best kinetics software out there. You could either automate the software and actually make the decisions for you, but in this case, what Alec did is he said, well, I do see 3 reaction events or 3 different events, and so then the software then of course picks the models. In this case here, an autocatalytic reaction was picked, and two nth order reactions were picked. The Kinetics Neo has many other methods available, and they're listed right here. We of course use the Friedman to do some of the evaluations, and I can show you here in a second how we did the analysis. So basically, you have the reaction rate as a function of the reaction, and an Arrhenius function with an activation energy. So the Friedman analysis, we take the reaction, we look at it in a logarithmic scale, and so we create a linear function, and from that then we can determine the different slopes. So if we plot the log of the system as a function of the reaction rate as a function of 1 over temperature, we get curves that can easily characterized. The other thing that we can do here in this case is, as a function of reaction rate, we can find the different activations energies. And so when the software looks at the different events, it looks where in the reaction it is, and it chooses then an activation rate according to the Friedman analysis. And for this case, it worked quite well. If we plot the conversion as a function of temperature for the different tests, now this is the integral earlier. So earlier I showed you the reaction rate, or actually the heat rate, but the heat rate is proportional to the reaction rate. If we integrate the reaction rate, we get conversion, which goes from 0 to 1, and we go then from 0.5 degrees Kelvin per minute all the way to 5 degrees Kelvin per minute. And the lower rates, of course, they're a little bit harder to capture, but this is really good, actually. I mean, that's where the largest error comes into the picture. In the beginning of the reaction rate is a little bit harder to capture, but this is a very nice fit. So we use then this model and you can see the correlation here is 0.9959. And so we use this fit now to model the actual process. So we started out with the original cycle, which is here, and then we varied different things. So the original cycle had a maximum conversion rate of 0.6% per minute, and it had a maximum heating rate of 1.2 degrees Kelvin per minute. So that's based here. And so we did all kinds of different analysis. So here's where Alex started playing with the software and also doing some optimization. And so at the end, you can see we had one that was relatively short, maximum conversion rate of 2.4 and 5 degrees Kelvin heating rate. And so we then here we cured then several parts. So this is optimized. Then we do that. We apply these optimized heating cycles to actual plates. And in our case, we made little plates of 40 millimeters by 12 millimeters by 2 millimeters, 2 millimeters thick, because we're going to apply these to parts that were about 2 millimeters thick. Now, if it is a thinner part, obviously you can have higher heating rates without raising too much the temperature in the center of the part. Or if you have really thick parts, of course, you need to adjust it to that. So the thickness of the part here, the 2 millimeters, is what was important. And then we place these plates in a DMA Eplexor, which is made by Netsch and Gabel, that has actually the feature here that may just look to you that it's like any other DMA machine. But if you look at these numbers here, you can see that we can have up to 500 newtons, and 500 newtons is a very large force when you talk DMA. And you have a very high temperature range. And so what we did is we placed these plates in here, and we then, with a heating rate of 2 degrees Kelvin per minute, and I believe he did the analysis at 1 hertz. I'm not sure, but I believe it was 1 hertz. And so here you can see the storage modulus and the loss modulus. So the storage modulus is basically the elastic portion as a function of temperature. It's relatively constant, and then it starts dropping off at higher temperatures. Where the slope is highest is where probably where the TG is, so the glass transition temperature is. But if we also plot the loss modulus, which is the damping in the material, you can see the scales here are a little bit different. They're about a tenth. There's a tenth here to the scales on this side. Where the peak occurs, the maximum point is where the glass transition temperature is. And so what we noticed here is that the 0.6 maximum conversion rate and 5 degrees Kelvin per minute maximum heating rate, that one matches the original cycle. So you can see the original cycle is right here, and this one right here, the one with the little green lines, is the one that matches it best. So the original cycle, we had a glass transition temperature of 154. The one that we chose to optimize also has exactly the same glass transition temperature, and both of them have within the error of the experiment the same ultimate strength. And so that's great news for anyone who wants to manufacture parts with this, because we can compare then our original cycle, which is the one recommended by Carbon, and this is the one that we optimized to make parts that actually had exactly the same properties, were just as good, and we reduced more than 9 hours of the 12.5 hours. In other words, we reduced the cycle time to a quarter of what we had originally. So that's one great application. Basically, you need, and you saw what steps we use there, but I think critical here is having accurate differential scanning calorimetry analysis with this software that can actually predict the reaction rate. And why do we need to have this? For example, we are using these materials 3D printed with a carbon system to create hybrid structures. And so this hybrid structure here, this would be, for example, a wing skin, which has spars between, or ribs between. When you place the prepregs right here on the wingspan, and where the prepregs come together on the other side to create the rib, you create a hollow region, which is called the deltoid. And this is, of course, this weakens a wing skin or weakens a part. This would be a T-joint, right? But it would look in a part like this. And so the idea behind, and there are different ways to fix this. So one of them is you roll up a prepreg like a little cigar, and you place it in where the hole is going to be, or you fill the gap with epoxy resin. The idea was, well, why don't we see what the shape of the deltoid is, and then 3D print the deltoid itself with a DLS process, and then we place it inside. Here you can see it. We put in the prepregs, put it in an autoclave, and cure it all together. And so here then what you, of course, this part here is trivial because you we can't deform that part that much, but in an autoclave the 3D printed part is relatively is relatively critical, because as you heat it up it becomes weaker, right? As you heat up the UV cured part, it loses the modulus, and so you want the curing to occur at just the right pace, so that you don't warp or deform that part. And at the end, of course, they co-cure, creating a great bond between the DLS part and the pre-preg. Then here's another application. This one here you have a DLS bicycle seat, that of course needs to be strengthened, especially this part right here. When you sit on it, it will bend quite a bit, and so here you can see the pre-preg is added on top. So when this is put in the autoclave and in the vacuum on where the pre-preg is vacuum on the 3D printed part, at the end you want perfect bonding, and you don't want to deform the DLS part. And here you have a brake a brake handle for a bicycle. So these are just some applications. This one right here, is kind of cute. We worked with Dark Arrow. I forgot the name of the bike company that we worked with. So Dark Arrow is a company in Madison, Wisconsin, that was founded by 3 of our students, and they're building an experimental aircraft, a 2-passenger aircraft. And so we've helped them with a lot of parts and a lot of their processes. This is a bell crank, where you can see the part here is the 3D printed. The general structure is 3D printed with DLS, and then you can see the pre-preg on it. And so you have a really strong part, but most of the shape then is from the DLS process. Here we have the experimental aircraft. They're almost done. And for the experimental aircraft, they use a lot of sandwich structures. And one of the issues they have is, okay, some of the structures are under the hood, so they can heat up quite a bit. And so they wanted to know, well, what are the thermal properties? How is the strength of the part of the modulus of these sandwich structures as a function of temperature, and then to decide which sandwich structure to use. And so we again use the Eplexor to do a DMA analysis, and this can really, these are relatively, first of all, they're relatively large parts. You can see the length of these are 50 millimeters. The thickness well, we have two different thicknesses, 12.7, 6.4 millimeters. But to test this, it requires quite a bit of force, and a regular DMA would not be able to do it. Here we require much larger forces. So we wanted to compare the aluminum core. So you have the pre-preg epoxy carbonate pre-preg on both edges, and one of them is an aluminum core at 0.5 inches thickness, an aluminum core with 0.25 inches in thickness, and then there is an aramide or a Kevlar core that is coated with phenolic, which is right at the center again with the prepregs on the sides. And then we did the analysis to measure the storage modulus and the loss modulus. So there's the loss modulus is the little red dots, and then the storage modulus is here. And again, we can see the stiffness relatively constant. That's what we want, up to a relatively high temperature range. Here you can see the glass transition temperature, 0.25, 0.5. 0.5 is just a little bit, since it's wider, it's going to measure a higher, obviously a higher stiffness because of a higher area moment of inertia, but you still will get the same TG or the same temperature thermal properties. Interesting is the aramide one, or the Kevlar one. We recognize here the glass transition temperature of the epoxy and the prepreg, and then you recognize the phenolic aramide glass transition temperature here, the drop, which occurs at 280 degrees C. So this one actually retains the properties quite well, even to very high temperatures. And it's, of course, a lightweight structure. So that one is about the 3D printing and hybrid structures. And I had one more, and I think I still have some time here. And this is natural rubber characterization. And I'll go maybe a little bit quicker through this. And Peter, tell me if I have to stop or something if I'm going over time here. Natural rubber is a fascinating material. Each one of these trees, you can see the trees here, the rubber is being collected there in these containers. You can see here the tree is being tapped. This is in Colombia, in South America. I'm originally from Colombia. And you can see here we're collecting the latex. So each one of those trees is really a polymerization plant. And so we hopefully will work with footwear manufacturers to actually start using natural rubber. So if you look at the natural rubber tree, right, a natural rubber tree, let's say, produces 1 kilogram of isoprene. Each tree produces, I would say, about 10 kilograms, at least 10 kilograms of polyisoprene or natural rubber per year. But to produce 1 kilogram of isoprene, the tree sucks in 1 liter of water. It breathes in 3 kilograms of CO2, and out of the exhaust pipe comes out 3 kilograms of oxygen. This couldn't have been the more sustainable polymerization plant. So this is just a little pitch for natural rubber. And so one of the things Alan and I wanted to know is, well, if we're going to use these for footwear manufacturing, there's a lot of variation and variability in natural rubber. For one, if we look at different samples at different times of the year, we have different rainfall for those times. And the question is, does rainfall have an effect in the final property of the rubber? And so we used characterization, material characterization, to assess that. The first thing that we did is we used our Polyma Netch system to measure the crystallinity in the rubber. Since rubber has a glass transition temperature of about minus 60 degrees C, and room temperature is is way above that. At room temperature, over time, rubber will crystallize. And the question is, does that degree of crystallinity, is that related? The degree of crystallinity affects the properties of the material, but also it affects it can be eliminated when you do a heating and a cooling. Obviously, it will disappear. But that's an interesting effect in rubber. And so we measured then the crystallinity or the endothermal peak of crystallization, and we plotted the energy joules per gram per each sample together with the rainfall. And there definitely is a correlation between rainfall and crystallinity of the natural rubber. That was interesting, but it also helps us if we have a rainy season. Well, then we know what to expect of the material, so we can characterize. If we generate enough data, eventually we can use, for example, machine learning and artificial intelligence to be able to generate different formulations. So at the end, we always have the same formulation, and we always get the same properties particularly if we're going to make athletic shoes with it. So the other thing that we wanted to do was to test the viscoelastic properties, and that we used Netch's Eplexor system and fixture. So Netch actually made this special fixture to do this type of analysis, and this is a double shear. So when we test this, these two rubber samples, it's a symmetric system, so we don't get any moments in the machine, and so we actually measure what happens in the system. I don't know if you see them. This one here is cycling at 1 hertz. This one here is cycling at 5 hertz. So we did 1 hertz and 5 hertz to kind of emulate maybe walking and running. And then we did 10% strain, 30% strain, and 50% strain. And this is interesting. And when people say, oh, DMA, and you're using 50% strain, you're going into the nonlinear domain. Well, yeah, we want to go into nonlinear domain because a shoe, an athletic shoe, a rubber tire, any rubber part will have high deformations. We never stay in the linear elastic domain. We always go into the nonlinear high deformation domain. So in these cycles, then, what the Epixor does to us, it stores the stress and the strain. If we plot the stress as a function of strain, we get something that we refer to as Lissajous curves. These are, or you can see the hysteresis loops or something. A lot of people refer to them as Lissajous curves. And the Lissajous curve is we have the philosophy that the Lissajous curve reflects what the athlete feels with the material. And here, right now, you don't see it as well. I see it. I see what I see here is that even at 50% deformation rate, we have is still a relatively linear elastic material. So we can compare again different times, December to September. And you can see, first of all, we can see, and here we see 50% and 30%. You can see a slight difference in the behavior, mechanical behavior, but they're relatively similar. The behavior, that behavior doesn't change much as a function of rainfall. But if we take this curve, let's take this Lissajous curve in June 2018, we can normalize it in stress and strain. So all the curves now, everything goes from -1 to 1 and from -1 to 1 in the stress. You can see they all fall one on top of the other one, relatively close, which means that at 10, 30, and 50%, we still have a very similar linear elastic behavior. As long as this curve stays like an ellipse, you're still the material behaves like linear elastic materials. This is great news for somebody who's manufacturing a shoe, an athletic shoe, because that means a person that is heavier or lighter and will deform the material more or less, but its behavior is still linear elastic. So we can, the other thing, the damping is relatively low. Here you can see both the September, two different 1 hertz, and 1 hertz is the higher damping, 5 hertz a little bit lower damping, but relatively constant damping as a function of deformation, which is also important. Other things that we did were relaxation tests. Also with the Epixor, we measured relaxation at different temperatures. Then we used the time temperature superposition principle to get relaxation behavior to very, very long time. So we don't need to do the test as long as we want the relaxation time by generating a master curve. And this is just standard viscoelasticity, a time temperature superposition. Here we have a relaxation curve at 30%. Obviously, 30% strain gets a higher initial stress, 10% a little a lower initial stress, and we can normalize it into the maximum stress, and we can see that this natural rubber material actually, no matter if you deform it a lot or a little bit, its relaxation behavior is the same. So which is good news for athletic shoe designers. The other thing is the temperature behavior. We wanted to see if the temperature behavior is related to rainfall. And so we fit the curves. So this B term right here is the temperature dependence. So the change of the slope with respect to temperature, we call that A. And A, we plotted as a function of rainfall. And you can see that the temperature behavior, or how temperature affects the elastomer, this elastomer material, is directly related to the rainfall, which is also really interesting. I mean, this is because then if all we need to do is record rainfall, and we already know what kind of material we're going to get and what behavior we're going to have. So we can either match, or we can create blends that generate a homogeneous material. This is a little bit, just a little insight. So these were measurements that we did with Ultra Boost. Ultra Boost is the Adidas shoe. It's a foam material with varying strains. So we have a 30% strain and 50% strain, and you can see they're not ellipses. I mean, this is a great material for an athletic shoe. It is very elastic. It doesn't have much damping. So they're very skinny, at least as U curves, but they are nonlinear, right? So if we compare now the Ultra Boost at 50% and 10%, it becomes nonlinear as we deform the material more and more. And we could also now compare the Ultra Boost with the natural rubber. You can see the red ellipse is the natural rubber. You can see how much linear it is. It's a perfect ellipse compared to the Ultra Boost material. The other thing that you can see is they actually have very similar elastic modules. I mean, even if we normalize it, we would get similar curves. But this is interesting. It's exciting. And the thing is, to be able to take these large rubber samples and deform into 50, maybe 100%. We could also do. You actually need a lot of force. So this here is where the 500 newtons of the Eplexor equipment really come into the picture. To be able to do nonlinear viscoelastic testing, the higher you go into the nonlinear domain, the higher forces you require. So eventually, of course, one of the ideas that we have is once we've characterized this material also through other aspects, maybe what we can do is 3D print some midsoles and generate some athletic shoes that can compete with petrochemical materials, and maybe in a very sustainable way. So anyways, I'm glad I had you here this afternoon, and this brings me to the end of my presentation. Thanks for your attention. I hope I didn't go too fast, did I?
You did wonderful. Thanks, Tim. I appreciate that. Everybody, I believe everybody can hear me now.
I can.
Okay, great. So I appreciate this. I'm going to switch over now from the sharing, Tim, and put it back on mine.
And were there any questions? I don't see them in the questions thing.
Yes, we do have questions.
Oh, okay.
So I will go ahead and ask those questions for you. We have the first question. How does the Friedman model compare with the Ozawa model described in the ASTM?
We did not do a comparison within the Friedman. The nice thing of the Friedman model, and I think all of them, I think it's a matter of preference, right? I mean, and Friedman is nice because you can very easily get the activation energy. Well, you still can get it with the other ones. I mean, even regular fits. I think one of the listeners is Nora Catalina Restrepo, and she did a nonlinear regression fit to get those constants. But yeah, I think a lot of it is a matter of taste. But I mean, they are available in the software. I think, and I believe Alec did not play around with them. He just used Friedman. He may have done it. I don't know. Maybe if he's in the vicinity, he can chime in.
Thank you. The next question says, why was not the coefficient of thermal expansion of the printed materials evaluated?
Oh, why wasn't? Yeah, good question. We do have a system that measures a PVT curing reaction where the volumetric shrinkage can be evaluated. Yeah, I mean, I think it's just a matter. I mean, there are some things that I'm not sure why Alec didn't. Maybe he's in trouble now that he didn't do that analysis.
Okay, thank you. And the next one, I'm going to read this, see if I get this correct. Would this work well for something Alvin Toffer coined prosumer, which custom tailored shoes for customers?
Yeah, I think, I mean, for example, even I know Adidas has different geometries that they 3D print. In fact, they use the DLS system, so you can design different structures that will behave differently, and those can also be analyzed using a DMA. I mean, that's basically, I think that the Lissajous curve that you saw is basically cyclically loading your sample. In shear, I find it easy because you can then transform the shear into elongation. But if you do the cycle, if you do a cyclic strain and then measure the stress and plot stress as a function of strain with any material, it will give you a great picture of what happens. So basically, any material, any polymer that is used for shoe manufacturing, and it will give you in essence, it will give you what a person will feel.
Wonderful. That's all the, let me see, just very down here. Okay, we have a few more. I'll get to one more. Can the kinetic software convert the non-isothermal kinetics to isothermal kinetics?
Oh, yes, and that's a whole other area. There is also this DSC can do a very fast heating sample, and we can go up to even 150, 180 degrees C in no time and do an isothermal analysis. And the software will take care of any losses that occur during the initial heating ramping, the fast heating ramping. So yes, and we've actually done a lot of work on that when we did some analysis of epoxies. So that was the PhD thesis of my graduate student, John Puentes, and we've actually published this work together with scientists at NETCH. So that we've tested that, yeah, isothermal. The equipment and the software is perfect for that. But of course, you need the equipment, right? You need to have something where you can ramp it up fast enough to reach the high temperature.
Sure.
Yes.
And from Alec, he did say, I did conduct the thermal expansion experiment. It's just not included in this presentation. And he did comparisons between all the model-free methods and the Kinetics Neo software that you're using. Does make it very easy to do all this. You just select the model from the software. So we did do that. And of course, if there's more discussions on that, you can contact Professor Oswald directly and get that information from him on that. And we have time. I think we just got, let's see, I'll ask this quick. We do have a few more minutes left. So I'm curious, the dual curing mechanism, does the UV curing degree affect the thermal curing efficiency?
So can you ask that again?
Well, he's curious if the dual curing mechanism, does the UV curing degree affect the thermal curing efficiency? In other words, will the second thermal curing cycle need to be changed?
Well, that's a good question. I mean, I think one of the things is, one thing that happens when you do the thermal curing is the bonds of the UV curing, some of them open up. And so what you need to do is to actually, if you heat it up too fast, you're basically going to melt the material. So you need to heat it up at a rate at which you still have enough strength to hold it apart, but what eventually will hold it apart in place primarily is going to be the second curing stage. That's what will cause it. And we have with this, I don't believe we have done the DSC analysis of the UV curing portion to compare the two. But most of the curing, of course, takes place in the heating cycle at the end.
Okay, wonderful. And that's all the questions we have for you, Tim. I wanted to thank everybody for joining. If you have a question or for some reason your question was not answered, you can feel free to go ahead and send us an email at, it's listed on the screen at nib_sales@netch.com. You can also visit our website at netch-thermal-analysis.com. And our upcoming talks, one is next week on metals, and the one in 2 weeks is the thermal analysis of advanced nuclear materials. And so if you'd like to sign up for these, you can go to our website or check your email that you received for this one, and there'll be additional information on there. I want to thank Professor Tim Oswald from the University of Wisconsin in Madison for his presentation today. And again, thank all of you for joining us today at our first Research Spotlight series. And we look forward to the upcoming talks. And again, any questions, please let us know. Thank you, and everybody have a good and safe day.
Thank you, Peter. So Peter, do you want a copy of my presentation in case somebody wants it, or?
Yes, that would be wonderful.
Okay, I will send it to you then. Thank you.
Okay, Tim, thanks.
Yeah, take care. Bye-bye.
Bye.
Let's see how to exit here. Maybe the easiest if you kick me out.